Welcome to the 7th Annual Dark Sky Festival in Sequoia and Kings Canyon National Parks. We are excited to bring it to you virtually this year. The purpose of the Dark Sky Festival is to provide an opportunity for people to create a lasting connection to their night sky. While the pandemic has been challenging, we still wanted to honor this purpose and bring the stars to you this year. My name is Scott Reinhardt, and I am a senior naturalist for the Sequoia Parks Conservancy, the official nonprofit partner to Sequoia and Kings Canyon National Parks. Throughout the year, my team and I provide telescope astronomy tours here in the parks. And when we look at planets, they seem to wiggle and warp like they're underwater. This is due to atmospheric disturbance. To get around this and other earthly phenomena, NASA sent up the Hubble telescope about 375 miles above the Earth's crust to capture unfettered deep space images. Now, almost 30 years later, the scientists and engineers at NASA are readying to send up Hubble's new and much larger sibling, the James Webb Space Telescope, which will allow us to look even deeper into the history of our universe. Here to talk to us about this amazing new piece of tech is Dr. Jonathan Gardner, who serves as the Deputy Senior Project Scientist for the James Webb Space Telescope, as well as the Chief of Laboratory for Observational Cosmology in the Astrophysics Science Division of NASA's Goddard Space Flight Center. Jonathan received his bachelor's degree in astronomy in astrophysics from Harvard University and earned his master's degree and PhD in astronomy from the University of Hawaii. A few of the projects that Jonathan has worked with include an infrared camera for the Spitzer telescope and a spectrograph imager and refit for the Hubble telescope. While he is interested in studying how the first galaxies formed in our universe, he also likes to perform folk music with his band and serves on an education advisory committee for his local community. Welcome, Dr. Gardner.
Very much for that kind introduction. I'm going to turn on the slides right now. Okay, I'm going to tell you a story. It's the biggest story there is, the story of the entire universe. It started 13.8 billion years ago with the Big Bang. The Big Bang saw the initial formation of all of the matter, energy, and structure that makes up the universe. It started out very hot and dense, but it was not perfectly uniform. Some places were hotter and denser than others. Those places started to accrete additional material through gravity and built up over time to form the first stars and galaxies in the early universe. Over time, galaxies merged together to form the spiral and elliptical galaxies that we see today. One of those galaxies is our own home, the Milky Way. Within the Milky Way and within the galaxies, stars and their planetary systems continue to form. Some of those planetary systems have small, rocky planets. At least one planet that we know of has liquid water on its surface. That planet has life and intelligence. So when you talk to astronomers will use three words. You'll find that they use three words a lot. We now know. And the reason that astronomers use these three words is because we now know things like proof of the Big Bang, the age of the universe, the fact that 95% of the matter and energy of the universe does not appear on the periodic table. We've detected gravitational waves, rocky planets around other stars, and so on. And these are things that astronomers working today can remember when we didn't know all those things. Astronomy is going through a scientific revolution due in part to the launch of the Hubble Space Telescope in 1990, the advent of large 10-meter class ground-based telescopes, and the use of supercomputers to model the theory of the stars and galaxies to match these observations. So in this scientific revolution, we have learned so much about our universe. And I'm going to be taking you in this talk through several of these recent discoveries and show that how they are setting up the future of what we're going to learn in the next 10 or 20 years. So starting off with the type of exploding star called a supernovae. There are several types of supernovae, but one special kind consists of a dead star, a white dwarf star, that's accreting material from a companion. And as this material falls onto the surface of the white dwarf star, it eventually reaches a critical level when the star explodes. The inner part of the star will collapse into a neutron star or a black hole, while the outer parts are blown out in a tremendous explosion. This explosion causes the star to outshine its galaxy for several weeks to a month. And when that happens, the explosion always happens at the same brightness level. So when we observe one of these supernovae with our telescopes, we see how bright it appears to us, and we know how bright it is intrinsically, and so that can tell us how far away it is. And by measuring the distances to these distant galaxies, we can build up the history of the expansion of the universe. In 1998, astronomers using these types of supernovae discovered a very surprising result, that the expansion of the universe was getting faster. And this was surprising because gravity should be attracting everything in the universe to everything else and slowing down this expansion. So this was the discovery of something was pushing on the expansion of the universe, working against gravity as a sort of anti-gravity and causing the universe to accelerate, to get faster. We have, this allowed us to build up a picture of the constituents of the universe. As I said, only 5% of the universe is made up of ordinary matter. That's stars, gas, planets, people, oceans, fish, so forth. That's 5%. 25 to 30% of the universe is made up of dark matter, which is an exotic particle that interacts with itself and with ordinary matter only through the force of gravity. There's no pressure, there's no electromagnetic forces, and so a dark matter particle could go straight through the Earth without interacting with any of the material in the Earth except through gravity. And then 65 to 70% of the universe is made up of dark energy, a very mysterious substance that is a fundamental energy of the vacuum of space that has a pressure that pushes on the expansion of the universe and makes it go faster and faster over time. The properties of the dark energy will also determine what the eventual fate of the universe is. Will the universe continue to expand, with the expansion continuing to accelerate, to continue to get faster and faster, to where all of the matter in the universe is pushed apart in a sort of a big rip? Or will the dark energy somehow turn around and start to be an attractive force and cause the expansion to stop, start contracting, and come together in a big crunch at the end of the universe? Any of these possibilities are many hundreds of billions of years in the future, so we don't need to worry about it. But it's interesting to know what our eventual fate will be. And NASA is working on future telescopes that will study the dark energy in more detail. About a century ago, Einstein put together his theory of general relativity, his theory of gravity. And one prediction of this theory was that there would be gravitational radiation much like the electromagnetic radiation of light. And when two very massive objects, such as two black holes, collide together, they would put out a lot of energy as gravitational radiation. For 100 years, we had a theory of gravitational waves, but only in 2015 did we first start actually detect the gravitational waves from two colliding black holes. And a little bit later, we saw another collision that produced both gravitational waves and light. So we turned all of our telescopes in the world on this one place and saw the flash of light that came from this collision. Back when I was in graduate school, there were no known planets around other stars. But in 1995, there was the first discovery, the first detection of a planet around another star. And now we now know about more than 1,000 extrasolar planets. When a planet will cross the face of the star and diminish the light from that star getting to our telescope, we can learn a lot about the planets. It's one way of detecting the planets in the first place. And then as the light from the star goes through the atmosphere of the planet on its way to our telescope, we can measure the constituents of the atmosphere. Here's a system of 7 rocky planets called the TRAPPIST-1 system, which is a very good target for future telescopes like the Webb telescope. And then last but not least, the outer solar system is, we have learned a lot about what the objects in the outer solar system. So much, in fact, that the discovery of Eris, which is larger than Pluto, triggered a discussion among astronomers about the definition of a planet. Do we continue to add all of these objects to the list of planets in our solar system? Or, in fact, the astronomers decided in 2006 that there would be a new class of objects called dwarf planets, of which Pluto is the closest. The outer solar system and the discovery of all of these objects out there will tell us about how our solar system formed, because these distant icy dwarf planets contain almost the pristine material out of which our solar system formed. And then we've also been spending a lot of time studying our sister planet, Mars, by sending robot dogs to travel around the surface of Mars with the rovers. And we have found evidence that there was liquid water on the surface of Mars as recently as 50,000 to 100,000 years ago. Right now, all of the water on Mars is frozen. A lot of it's in the polar ice caps or underneath the surface of underneath the rocky surface. But there is some very intriguing evidence that we may see things like mudslides or other evidence that even in very recent times there have been liquid water or very muddy liquid water on the surface of Mars. So all of these we now know discoveries have come about because of the Hubble Space Telescope, the first time we've put a very large telescope in space. That the launch of Hubble was in 1990, and 5 times since then, we have sent astronauts up to Hubble on the space shuttle to replace the cameras, upgrade the capabilities, do any repairs that were necessary, and Hubble has now been operating for more than 30 years in space. The faintest picture that humanity has ever taken was taken with the Hubble Space Telescope, and it's called the Hubble Ultra Deep Field. There was more than a month of exposure time taken in lots of little pictures that were added together in lots of shorter exposures that were added together in our computer to make this deep picture of the sky. When we looked with other telescopes at this patch of sky, we didn't see anything at all. But the Hubble was able to see that the universe is filled with galaxies. There are nearby galaxies, which are the kind of bigger and brighter galaxies we see in this image. And as we go further away, the galaxies appear to us to be fainter. The advantage of looking very far away is that we're looking backwards in time to when the universe was younger, because some of the galaxies in this Hubble ultra deep field were viewed when emitted the light that we see when the universe was less than 1 billion years old out of the 13.8 billion year history of the universe. So we're looking back to within 1 billion years of the Big Bang. And one of the things we see when we study these very distant galaxies in more detail was the surprising result that some of these galaxies fit theoretical models of star systems that were already several 100 million years old, which means that the most distant galaxies that Hubble can see are not the first galaxies that formed in this region of the sky. In order to find the first galaxies that formed after the Big Bang, we have to look still further away, and then still further backwards in time to see the origins of the stars and galaxies. But there's another thing that means that we have to go beyond Hubble. As the light travels from these very distant galaxies through the expanding universe, the wavelengths of the light, the colors of the light, are stretched out so that light that was emitted as light we can see, visible light, or in the ultraviolet, is stretched out and pushed into the infrared. Now, most of the sun's energy that reaches the surface of the Earth is visible light. This is not a coincidence. We evolved to be able to see the light from our primary star. But infrared is heat. It's heat radiation. And as you go beyond visible light, you start to see temperatures. So in this image of a person down here, we have a man who's wearing a tie, wearing sunglasses, and holding a lit match right here. The coolest parts of this picture are the parts that are away from the person's body, the tie, the sunglasses. The hottest point is the flame of the match. Here we have a picture of an infrared picture of a cat. Again, the fur is cool. The eyes and the mouth of the cat are the hottest points because they're close to the inside of the cat's body. And in this final picture down here, we have a visible light picture of the floor where somebody used to be standing barefoot, but they walked away. When we look in infrared light, we can see the warm footprints that the person had left behind. So in order to go beyond Hubble, we need a telescope that is bigger, that can see further, more distant objects, and we need a telescope that's optimized to view in the infrared. Now, because infrared is heat, we need a cold telescope, because a warm telescope or a room temperature telescope like Hubble or like telescopes on the ground are emitting infrared light themselves, and that light will outshine the stars and galaxies that we're trying to detect. So in order to see the first galaxies that formed in the early universe, we need to have a telescope bigger than Hubble and colder than Hubble. And that led to the design of the James Webb Space Telescope. The science of Webb, that Webb was designed to do, includes origins and evolution. Origins are important because when you see how something starts out, you can set your model of explaining how it came together. But evolution over time, changes are also important. So Webb's science goals, or 4 science themes, include the origins of the first galaxies that formed in the early universe, how those galaxies changed over time to be what we see in the modern universe, the formation of stars and their planetary systems, and the study of other planets, both planets around other stars and planets within our own solar system, for the origins of planetary systems and for the conditions that might enable life on those planets. So taking a little bit more detail, this is a supercomputer model of the formation of the early galaxies. As I said, small, dense parts of the universe started to accrete additional material from other things around them and build up over time to the point where the first stars could form. But these first stars formed in very small galaxies. And over time, these small galaxies started colliding with each other and building up to being larger galaxies. Many galaxies today live in groups like this quartet of 4 galaxies. And when galaxies get close to each other, they sometimes will collide. This is another supercomputer model of the collision of 2 giant spiral galaxies. Our own Milky Way is a giant spiral galaxy, as is our nearest neighbor, the Andromeda galaxy. And someday, perhaps the Milky Way and Andromeda will collide like this. But we don't need to worry about that, because when galaxies collide, they don't go bang, they go slosh, because most of a galaxy is empty space in between the stars. And the stars in colliding galaxies will interact with each other just through gravity, and very, very rarely would they actually collide. So this collision of 2 spiral galaxies taking place over hundreds of millions of years in this model ends up sending a lot of the stars out into intergalactic space. But what is left over in the center is something that looks a lot like an elliptical galaxy. And likewise, when an elliptical galaxy is kind of left alone for a while, it will accrete additional gas and form a disk and start to form stars within that disk. So spiral galaxies and elliptical galaxies can go back and forth over time. When spiral galaxies collide with each other, they become an elliptical galaxy. When elliptical galaxies accrete more material and form new stars, they can end up looking like a spiral galaxy. Within our own galaxy and in other galaxies, stars continue to form. Stars form in clouds of gas and dust, mostly hydrogen, which makes up most of the universe, but there's also helium and other elements. And then the dust is things that eventually become planets, carbon and iron and the other harder elements. When a star forms, the dust can collapse into a disk, and then concentrations within the disk can start to build up over time and become rocks and eventually merge together to start to form planets. When a young solar system has with its planets, sometimes the planets can be in very similar orbits. And in this is just an artist's conception of the very early solar system, when the very early Earth was impacted by another planet about the size of Mars. This collision filled the whole solar system with dust, and some of that dust coalesced around the early Earth to form the moon. And this is the leading theory of the origin of the Earth and the moon, that the early Earth was impacted by another planet, and that formed the moon. In some other solar systems, around other stars, we see giant dust clouds that were indicative of a recent planetary collision like this. So now I'm going to show you a comparison of some of the properties of the Hubble Space Telescope and of the James Webb Space Telescope. Now, as I mentioned, Hubble is a room temperature telescope. It's in orbit around the Earth in what's called low Earth orbit, and it goes in and out of the sunlight every 90 minutes. It's on the daytime side for half of the orbit and on the nighttime side for the other half. So when it's in the sunlight, it warms up. When it's on the nighttime side, it would cool down, but we actually run heaters to keep it at a constant temperature, because otherwise the going from hot to cold every 90 minutes for 30 years would put a lot of stresses into the telescope. Also, when the astronauts go up there to do their servicing missions, we don't want a very cold telescope for the astronauts to sort of freeze to. Hubble was designed to be kept at room temperature, but in order to work in the infrared, the Webb telescope will be cooled to 225 degrees below 0 Celsius. That's minus 370 Fahrenheit. Very, very cold. And it's kept very cold by putting it behind a tennis court-sized 5-layer sun shield that protects it from sunlight. This is one of the layers of the sun shield, with a person in the middle to show you the scale of this the sun shield. Hubble is in orbit at what we call low Earth orbit, about 375 miles above the surface of the Earth. That's as high as the space shuttle would fly. And as I said, it goes around the Earth every 90 minutes. Webb will be put into a special orbit in deep space 1 million miles from the Earth. That's 4 times the distance of the moon. The launch of Webb will be next year using an Ariane 5 rocket, which is part of the European contribution to the mission. Webb is a partnership between NASA and the European and Canadian space agencies, and the Europeans are contributing the launch of the rocket. Webb will go to a special point called the second Lagrange point, in which the Sun and the Earth and the telescope will always stay in a line. As the Earth goes around the Sun once per year, the telescope will keep track with the Earth and keep the Sun and the Earth all lined up, so that the sun shield can protect the telescope both from sunlight and from reflected light from the Earth and the moon. And then finally, in size, Hubble's primary mirror is 2.4 meters, just a little bit bigger than a person. Webb's primary mirror is 6.5 meters in diameter. Webb's primary mirror is made up of 18 hexagonal mirror segments to make it easier to build. Now, I told you that Webb will be launched in an Ariane 5 rocket, and the Ariane 5 is 5 meters in diameter. So it brings up the question, how do you fit a 6.5 meter space telescope into a 5 meter diameter rocket? Well, the answer is you fold it up. So here's a computer model of what will happen after Webb is launched next year, as we've gotten rid of the rocket fairing and we will start to unfold the telescope. The first things that came out are the solar panels for power and the communications antenna. And then we need to start to unfold this tennis court-sized sun shield. The telescope and the the sun shield are separated, and now the covers of the sun shield are folding back on both sides, and we will start to pull out the layers of the sun shield. The sun shield is made of kapton, which is a plastic material, sort of like garbage bags, but coated in a highly reflective coating so that the bottom layer of the sun shield will reflect the sunlight, and each successive layer will allow the heat to escape, so that there's very little of the sun's energy going into the telescope. The final deployments are the secondary mirror and the two side wings of the primary mirror. All of these deployments will take place in the first 2 weeks after launch, and then the telescope will be on its way to the second Lagrange point. I'm going to show you some pictures of some of the hardware we have for the Webb. These are the primary mirror segments being inspected by a technician. Primary mirror segments are made of beryllium and coated with gold. Beryllium is a very lightweight metal, and gold is very reflective in the infrared. This is how we assembled those mirror segments onto the backplane support structure. They were assembled with protective black coverings on the mirror segments, and they were assembled using this robotic arm, and the technicians were attaching each mirror segment as it was placed down. The last mirror segments to be attached were on the two side wings of the telescope. Here's a picture of the fully assembled mirror in the clean room at the Goddard Space Flight Center where I work. And this is the coolest selfie I will ever take in my life, where I was able to take a picture of myself reflected in the primary mirror of the James Webb Space Telescope from the viewing window. After the telescope was fully assembled, we installed the cameras onto the back of the telescope. There are 4 cameras on the Webb which will be able to take pictures in the infrared and also do spectroscopy. And the cameras were built by various organizations. There's one camera that came from the Europeans, one that came from the Canadians, and then they each have different capabilities. This is a time-lapsed video of the installation of the instruments onto the back of the telescope, and I was fortunate enough to be in the viewing window when this was assembled. After the telescope and instruments were all put together, we took it to the Johnson Space Center in Houston for a vacuum chamber test. The telescope was tested in a giant vacuum chamber that was actually built for the Apollo program. And this vacuum chamber was originally human rated, and the Apollo astronauts practiced walking on the moon in their spacesuits in a vacuum in this chamber. But several years ago, the Webb project took over this chamber and modified it to go very cold for the operating temperature of Webb, and put it through a 3-month-long test to make sure that the instruments and telescope would work at the operating temperature and in a vacuum. Meanwhile, we were working on assembling the sun shield and the spacecraft at the facility of Northrop Grumman Corporation in Los Angeles. And then more recently, we assembled the telescope onto the spacecraft. Here's the two before they were put together. And then when they were put together, we can do a test of the deployment of the sun shield. Now, it has to be done on a tabletop because in space, there won't be any gravitational effects. And so in order to support it for the test of the deployment, we had to do it on top of a table. But there we have the sun shield is fully, the 5 layers are fully separated, and the telescope, the whole observatory is put together. Now that the observatory is fully assembled, we will do some final testing. We will simulate launch by blasting it with sound and shaking it on a vibration table that will simulate the sound and vibrations of a launch. And we are in the process of doing that right now. After those tests, that simulation of launch test, we will do one final deployment test to make sure everything still works, and then we'll ship it to the launch site, which is Kourou, French Guiana in South America. That's where the European rockets are launched. Now, if you'd like to learn more about Webb, we have a website, webb.nasa.gov, and we also, from that website, you can sign up for our Facebook, Twitter, and other social media. There is a huge amount of information about the assembly of Webb, the flight hardware, and also about the science that it's going to do. So I encourage you to go to webb.nasa.gov if you'd like to learn more. Here's a picture showing a couple of our fans on the set of The Big Bang Theory. They had a model of the Webb telescope back here and some of our pictures. Webb was designed from the beginning to contribute to the advancement of our understanding of our history, the history of the universe, the history of the formation of stars, galaxies, planets. Where did it all come from? And I'm going to leave you with a quote from Carl Sagan that is indicative of what we really hope for Webb. And that is that while I've told you what we built it to do, I hope that the most exciting discoveries that the telescope will make in the next 10 years will be things that we didn't expect, that we can't predict. New discoveries about the universe that astronomers will say, we now know. So I'll leave you with this. Somewhere, something incredible is waiting to be known. I'd like to thank you for listening to this talk.
Wow, thank you so much, Dr. Gardner. Just everything, all your insight and knowledge about the telescope that's going up there, that really was a pretty awesome selfie. I think that's a good one. That goes down in the books for sure. Yeah. And I'm so excited about not only the data and information that the James Webb Telescope will be able to provide scientists, but I'm also thrilled about the images that we'll be able to see and connect with, and how they will be able to not only bring the stars to us sitting at home, but also the first galaxies in our universe. It's pretty amazing. Thank you for sharing your insight and your knowledge with us. We look forward to seeing the James Webb launch, hopefully next year. And thank you so much. For those of you watching at home, thank you so much for joining us. I will be live with Dr. Jonathan Gardner on Saturday at 5 p.m. Eastern, 2 p.m. Pacific. If you have any questions for Dr. Jonathan Gardner about the James Webb Space Telescope, you can find all that information. That video will be playing here, sequoiaparksconservancy.org/Dark Sky Festival. Thank you so much for watching. We hope you have fun exploring the rest of the festival. We have interviews with engineers working on the Perseverance Mars rover that launched last month. We also have a star party where we will be looking at deep space objects through the telescope that we have here in Sequoia and Kings Canyon National Parks. We have fun information for all ages, and we'll be hosting a trivia night tomorrow, Sunday, September 13th at 6 p.m. Eastern, 3 p.m. Pacific. Thank you again for watching and for allowing us to bring the stars to you.